Welcome, everyone. It's really, really great to be here. I'm here to talk to you about how Docker supports tackling the localization challenge. So if you're not familiar with what localization is, it's okay, we'll go over it, but it's essentially, it helps you, if you're building any product, doesn't matter what product that is, it helps you to grow that global empire, to release things in other markets, and to grow a user base. So quick bio, my name is Michelle Casbon. I have advanced too many slides. So I'm head of data science at Qordoba, and the reason why this is such an exciting topic for me, why I really love my role at Qordoba specifically, is because my background is in, both my degrees are in computer science, and when I was a teenager, I lived overseas for a few years. I learned a second language. So combining the computer science aspect with linguistics, computational linguistics is one of my favorite things, and I get to do a lot of that at Qordoba. So that's what we're going to talk about today. The main point of this is just to talk about how there's a more efficient way to do localization and how Docker enables that. NLP models are really famous for they're notoriously hard to operationalize, to run in production, to support, to really operate in an efficient way, and Docker enables so much of that. So we'll talk about what the problem is and how Docker makes that better. So sorry, the clicker keeps moving forward. So what is Qordoba? You can think of it as sort of the Docker of content. The idea is really to take out your content and put that into a completely separate layer, because as we're all familiar with, if you can modularize things, if you can separate them out, it's a lot easier to work with them. And if your content is somewhere else, separate from your application logic, then you can be a lot more flexible with it. You can add a lot more languages into it, and you can separate it out into much smaller buckets. So that's the idea. This is just a diagram to illustrate that. The bottom layer, that's your bare metal. Above that, you have your Docker layer, your containers. Above that, you have your application logic, which is what you think of as whatever product you're building. And then completely separate from that, that's your content layer. So that's what we're talking about today. And as far as localization goes, if no one's ever had to tackle it before, it's a really, really messy process. It involves a lot of humans and a lot of communication between those humans. So the idea here is to really make that an easier process, to automate as much of that as we can. This spans a lot of teams. You have designers, you have marketers, you have engineering, you have DevOps, you have all these different people trying to talk to each other and work on the same things. And so if you can automate a lot of that, then you can make it a much more efficient process. So essentially, in your product, whatever you're building, you use an SDK and you point to, instead of actually writing in a string, you would have a link and it points to somewhere in the cloud, and then other entities can update that target. And that results in consistency among all of your products, whether it's a website or a mobile app. It's all updated live, and there's no hard-coded strings anywhere. So the other, where did the slide go? All right, here we go. Sorry. Okay, so the other thing that makes this really important for automation is a GitHub integration. That way, when your designer submits a change, engineers don't really care what's inside that. But if you have a GitHub integration, then the engineer can deploy that PR whenever is convenient. And by separating that out into another layer, you have less risk whenever you deploy your applications. So the goal here is really to just automate as much as possible. And this is where Docker comes in. So, okay, example time. Everyone here is familiar with electronic billboards. And so thinking about this localization problem, if you, let's say you own a produce company and you wanted to sell more watermelons. So this is a picture, this is in my neighborhood. I live in the Mission in San Francisco, and this is a really typical scene. So if I want to sell more watermelon, I'm going to go to an electronic billboard company and say, here's this really beautiful picture. I want you to deploy that in Dolores Park. Billboard company will go ahead and put that up there. I see my sales skyrocket. I'm a happy camper. But what do I do next? Well, I want to expand. So I go across town to Chinatown, and I tell them, okay, take that ad from Dolores Park and put that in Chinatown. And you see no sales movement whatsoever. Why? Well, that should be pretty obvious. What works in the Mission probably won't work in Chinatown. So you have an idea. Is anyone familiar with this story of Brother Orange? It's not super important, but he's essentially a symbol for cooperation between America and China. So if you wanted to put something in Chinatown, why don't we have Brother Orange tell people to buy things? So you put this out, you call up your billboard company and you tell them, look, here's my new ad, I've worked on this, put this out there, and your sales skyrocket. It's orange sales, not watermelon sales, but whatever, sales are sales. So how do you expand beyond that? You have these two wildly successful campaigns in your own city, in places that you go to all the time, but you can't really do that on a neighborhood by neighborhood basis throughout the city, much less the country or the world. And even if you could, how would you manage all of that? How would you maintain your watermelon ads versus your orange ads versus whatever? So that's the problem that we're trying to solve. That's what localization is. And so you really end up with these sort of subsets of content in lots of different areas. So it could be Chinatown, it could be the mission, or it could just be the difference between, if you're writing an obituary, you don't really want to have language that's coming from social media. So you have all of these different containers. So within your content layer, you have different containers. The platform itself, built on Docker, running in Kubernetes, it's really just containers all the way down. This is what's important to us. This is what we're trying to solve. So the project that I've been working on, I mentioned that I had a background in machine learning in NLP. The computational linguistics thing, that's sort of my focus. That's what I do at Qordoba. And so we're trying to automate this whole process, and the more information you can have about your text, the better your translations are going to be. So that's where affect detection comes in. It's okay if you don't recognize it, it's kind of an academic term, but it really just refers to understanding the meaning that's associated with a piece of text. So that's important because if we know the emotion associated with two translations, we have a pretty good signal as to whether that translation is accurate or not. And that helps with our automation process. That means that there are less humans involved in the process, and there's a lot less friction. So, example time. This is a sentence that we put into our affect detector, and if you would guess at the sort of emotion that might be spit out in relation to this sentence, what would you guess? What kind of emotion? Your choices are joy, sadness, anger, fear. What would you guess? Anyone? Excitement. I like that answer. So this was the answer that our machine learning models gave us. Trained on a corpus of data, we didn't come up with this, but it says something about the corpus, is all I'll say. So we changed one word in that sentence. We didn't even change the gender. We just changed the direct object. And we got a very different response. And those two sentences have very different meanings. So you can see that emotion is really important. Now, if we were looking at an actual translation, so this is, if I'm this produce company, I have been selling so much fruit, I need help. So I put up this ad. But I'm located in the mission. So I'm also going to be putting it up in Spanish. The English version of that might be associated with maybe sadness because I have too much work. But if I come up with this translation, it's roughly equivalent to get off your lazy butt and get a job. That emotion is going to be very different, and that would tell me something very important about the translation that my models had come up with, and that we would flag that as, hey, a linguist should look at this again. The third example, again, live in the mission, rent is completely outrageous. Let's say that I'm putting my apartment up on a vacation rental site. I mentioned that I learned another language when I was a teenager. That language was German. So I come up with this ad, and I really want Germans to come and stay in my apartment. It really is. It's on Valencia Street. It's a killer location. But the German translation that I get in my ad, diese Wohnung befindet sich an einem mörderischen Standort. Mörderisch means the same thing in German as it does in English. You wouldn't stay in an apartment that's in a murderous location. So I don't get any Germans coming to my apartment, and that completely defeats the purpose. So this is why emotion is so important. So how do we build? If we want that affect detector, if we're trying to automate all of this, how do we build it? Conceptually, if you aren't familiar with NLP, this is going to be your 5-minute introduction. I'm guessing a lot of people are infrastructure engineers, but this is just a pretty quick overview on what it takes to build that affect detector in order to get those emotions out. So there's a couple different components. The main one that we care about is this prediction box. So that's sort of our end goal. We're trying to predict the emotion associated with any given piece of text. But in order to get that, we first have to turn that text into numbers so that we can do something useful with it. The heart of NLP is really just fitting text to a mathematical model so that we can identify patterns. And that's how we come up with consistent results, and that's how we get the accuracy in detecting our emotions. So the first step is feature extraction, where you take that text and you turn it into some sort of numerical representation. In this case, it's just a vector of doubles, pretty standard. And from there, you go into the training phase, where you take pieces of text and then an associated emotion that you've sort of hand-labeled or gathered from somewhere. And that's where you fit coefficients for your mathematical model. And from there, you can do a prediction. Once you've built and trained a model, you can start predicting things. The first model I built for this affect detector was, I think, on Simpsons quotes or something useless, but it will work. It may not be that accurate, and so that's why you need to do cross-validation. That tells you how accurate your models are, and if you come up with results that are suboptimal, which is almost always when you first build a model, hyperparameter tuning is where you tweak those parameters so that your coefficients change and so that you can get a bit better accuracy. And so you kind of go through that loop over and over again until you get the results that you're looking for. So those are the 5 main components. Just a little bit more detail. The featurization step is where you take your text and you turn it into numbers. And the way you do that is you tokenize it, you turn that into just sort of the core pieces of the text, and you can just sort of count those up and say, how many occurrences of each word did I have in the text, and build a vector out of that. So very, very simple. It doesn't have to be complicated, just essentially your term frequency. The training portion is where you take that vector, you assign it a classification, which is essentially a motion. You're saying, okay, this piece of text in this vector representation represents the joy emotion. And you give it a lot of those, and you send it into a library. In this case, we use Spark's MLlib, and we say, do some logistic regression for me. And it spits out a model that we can then use to predict with. The cool thing about the way we're training our models is that we're auto-generating it using YouTube videos, because they have text associated with it, and then there's an API that spits out an emotion based on a face, and so we're taking photos out of the videos, associating it with the transcript. Anyway, kind of beside the point. The prediction phase is where you give it new text and you ask it, what emotion do you think this is? And that's where we would take each of the text, the Spanish and the English version, give it an emotion, and make sure that those match. And if it doesn't match, then we'd flag it for, hey, a human should maybe look at this. And we go through that entire featurization process, do the exact same thing, turning the text into numbers in the exact same way so that it's in the same feature space, so that it makes sense with the model that we've trained. And then we just send it to Spark's library. We say, this is our vector, and give me an emotion, give me a classification for it. The cross-validation component, that's where we look at how good our models are. And the way we do that is we split it up randomly into 10 different sets. Or 10 different sets of 2. We have a training set and a test set, and we run it through essentially 10 different sets of training and see how it performs. And with 10 sort of random splits of that, you should get a pretty good idea of how well your text will perform on data that it hasn't seen before. So that was a really whirlwind intro to NLP. That's what we're trying to build. We're trying to build a system that can do all of those things just for the purpose of giving us that prediction, giving us an emotion associated with a piece of text. And we had to fit that into a whole other platform. That's a platform that gives us, that's a platform that supports localization. So it's a Play app in Scala. It's deployed in the cloud. None of that really fits into those boxes. Is anyone familiar with this scene from Apollo 13 where they sort of dump a bunch of parts onto the table? That's really what it felt like. I had to build this affect detector using all of these different random assortments of things. It looks very jumbled, and this was a landscape that I had to fit all that into. So now you can see why Docker is so important, trying to do all of this in such a crazy environment. Essentially, it's very simple. There's a front end for the platform. There's an orchestration layer that calls all of the microservices, and I just had to build a microservice that could fit into that could be deployed in the same environment and talk to everything else. And this is what it looked like before. My affect detector did not fit into a Mason jar. It was a Mesos cluster. Everything would get built into jars. I couldn't do it in that environment. So Circus comes to town. I had to do something different. If you look at, so if I were just to run this locally on one machine, it would look something like this. If I were to build that affect detector in serial with all of those pieces, this is what it would look like. You load your data, you build your models, you train them, and then you deploy your prediction model. But those footprints look very, very different from one another. These are all sort of batch processes. That prediction is just something that you serve up that sits there and waits and provides a response. But everything else is batch. So if you And even within those two, your data load, you're really only going to do that once or maybe have a trickle feed. But then your model training, as you improve your models, you're going to be doing that over and over again. And that's your most intensive step. So what you want to do is break those out. So what we did is we built one Docker container. It had the same code in it, but we gave it different entry points for each of those pieces. And we moved those storage layers out of the Docker containers. And we essentially were able to put the computationally intensive pieces, spread those out over several different containers, and build lots of different models because we had that one Docker image with just different parameters, and put a router in between it. So now we could have a model that gives us English predictions, that gives us Spanish predictions, that gives us German predictions, everything. And we can sort of spread that out across very different node types because they have very different requirements. So what did that look like? We put that into a cluster. We happened to use Kubernetes, but because that wasn't just a cluster full of jar files, we were able to take all of those other jars and put those into Docker files and put it all onto the same cluster. So we get all of this beautiful homogeneity. We can run everything on the same cluster and get rid of a lot of other tools. I'll talk about that in a minute, but I wanted to sort of briefly go over what's in that image. This is that big monster image that does everything. It does the training, it does the data loading, it does the predicting, and we build everything from source. Spark, it has some native libraries, some linear algebra libraries that it needs to use. So we build everything from source. There's a lot of improvements we could make there, especially after having been to Abby's talk yesterday on having smaller images. But then for everything else, we have this sort of base image for all of the other microservices within our platform. That means that we can standardize using the same Java version. That means that our ops really has a lot less to do. It doesn't have to maintain all of these crazy environments. And then we just build all of those things that used to be jars. We build that on top of that builder file and deploy it all on the same cluster. So I mentioned that we had chosen Kubernetes. The reason we did that is just because we operate primarily in Google Cloud, and they have a managed Kubernetes cluster, and we basically do no work for it. We deploy a YAML, and that's kind of it. It was really, really easy to get up and going, but otherwise we could have chosen Swarm, we could have really chosen anything because we're not doing anything super complicated. But we were able to reduce that cost per customer from like 6% to half. That's a huge difference. If you're a startup, you really, really care about the resources that you're using in terms of time and just cost for VMs. And getting rid of a ton of tools by just moving into Docker, into Kubernetes was really huge for us. We were also able to, I think we had a DevOps person leave, and we kind of didn't notice because things just run so much easier. I shouldn't say that. I mean, we definitely noticed him being gone, but moving things over means that you have much less much less pain with him being gone. And it just makes everything a lot more obvious. You are a lot more cognizant of how your pieces are talking to each other, and so you can reduce your complexity significantly. Let's see what else. That also allowed us to get better coverage. We have customers all over the world, as you can imagine, and so people in Dubai, they want to have lower latencies. They don't want to be running off of things in the US, and so that gave us a lot of flexibility to really make things better. So I think I'm out of time. That was about it, but the whole point is just that Docker enables us to do so many things that we couldn't do. The field of localization really hasn't changed in 35 years. And why weren't we using machine learning before? Well, because it wasn't that easy. But with Docker, it really is easy. So if you guys have any questions, I don't think we have time for any, but I'll be around, and feel free to come find me if you want more details about what we're doing. But thanks, everyone.